Hi everyone, I am Roy. In my last voltage drop video, I mentioned that AS-NZS 3000-2007 contains a simplified method for calculating cable voltage drop found in Appendix C, paragraph C4 on page 376. Today we'll be guiding you through this method. This lesson is broken down into 4 sessions. Session 1, Introduction. Session 2, Detailed Steps and Examples. Session 3, Mock Exam. Session 4, Summary. Let's get started with Session 1, Introduction. Session 1, Introduction. In this method, we'll be using a specific formula to calculate the necessary cable size and voltage drop. Additionally, we'll refer to Table C7, which provides cable voltage drop values per unit length for different cable sizes. The formula is the product of the root length and the current divided by the percentage voltage drop is equal to 10 times the operating voltage divided by the cable voltage drop factor. L. The root length is the distance the circuit runs, measured in meters. I. The current is the amount of electrical current in the circuit, measured in amperes. Percent VD. The percentage voltage drop is the allowable reduction in voltage. VO. The operating voltage is the voltage at which the circuit operates, measured in volts. VC. The cable voltage drop factor is the voltage drop per unit length of the cable, measured in millivolts per ampere meter. Okay, now we look at Table C7, where the conditions of root length, L, and circuit current, I, are known. Table C7 can be used to determine 1. The required cable size for a specified percentage voltage drop in the circuit. 2. The percentage voltage drop that a particular cable will provide. Let's go through the detailed steps for each situation. Session 2, Detailed Steps. I will use example questions to go through each detailed step. Situation 1, finding the required cable size. For our first example question, we'll determine the minimum cable size needed. Let's say we need to carry 40 amps over a distance of 80 meters with a maximum voltage drop of 2.5% in a 230 volt installation. Step 1, we calculate the value by multiplying the route length and current, then dividing by the allowable voltage drop percentage dot. We find that the value is 1280 ampere meters per percentage voltage drop. Step 2, refer to Table C7. Referring to Table C7, we see that a 25 square millimeter cable's value is greater than 1280. So a 25 square millimeter cable is sufficient for this requirement. Answer: 25 square millimeter cable. For our second example, we'll determine the minimum cable size needed to carry 60 amps over 50 meters with a maximum voltage drop of 3% in a 400 volt installation. First, we calculate the value by multiplying the root length and current, then dividing by the allowable voltage drop percentage. This gives us 1000 ampere meters per percentage voltage drop. Next, we refer to Table C7. For a 3-phase 400 volt installation, a 10 square millimeter cable provides 1034 ampere meters per percentage voltage drop, which is sufficient. Answer: 10 square millimeter cable. Situation 2, finding the voltage drop percent. For our example, question 1, we'll find the appropriate cable size with its voltage drop percentage within the maximum allowed voltage limit to carry 35 amps over a root length of 30 meters using a cable in a 230 volt installation, with a maximum allowed voltage drop of 3.5%. Step 1, calculate the value by multiplying the root length and current. 30 meters multiplied by 35 amps equals 1050 ampere meters. Step 2, look up the ampere meters per percentage voltage drop value in Table C7 for trial cable sizes. For a single phase 230 volt installation, a 4 square millimeter cable has a value of 205 ampere meters per percentage voltage drop. Step 3, get the percentage voltage drop. Divide the value from Step 1 by the value from Step 2. 1050 divided by 205 equals 5.12%. Since 5.12% exceeds the maximum allowed voltage drop, we need to try a larger cable size. Now try a 6 square millimeter cable size. For a single phase 230 volt installation, a 6 square millimeter cable has a value of 306 ampere meters per percentage voltage drop. Calculating this, we get 1050 divided by 306 equals 3.43%. Since 3.43% meets the voltage drop limit, a 6 square millimeter cable size is sufficient. Answer: the voltage drop is 3.43%. For our example question 2, we'll find the voltage drop percentage for a three-phase circuit carrying 45 amps over a route length of 40 meters using a 10 square millimeter cable in a 400 volt installation. Step 1. Insert given variable values into the formula to get the product of the route length and current. 40 meters multiplied by 45 amps equals 1800 ampere meters. Step 2. Look up the ampere meters per percentage voltage drop value in table C7 for trial cable sizes. First, try a 10 square millimeter cable which has a value of 1034 ampere meters per percentage voltage drop. Step 3. Use the value calculated in step 1 and divide by the value from step 2. 1800 divided by 1034 equals 1.74%. Answer: the voltage drop is 1.74%. Session 3. Mock exam. Now it's time for you to practice. We've provided some demo mock exam questions to help you apply these concepts. If you need more questions, please contact your local polytechnic. I have shared all my Moodle questions with polytechnics across New Zealand, so they should be able to provide you with additional resources. Keep practicing and studying to ensure your success. To recap, we've walked through the steps to use the formula in table C7 to find the appropriate cable size and ensure voltage drop is within acceptable limits. Practice with the provided questions to reinforce these concepts. Stay tuned for our next video where we'll discuss maximum demand calculation for the EWRB Electrician Regulation exam. This is another crucial topic for your electrical studies 2025. Good luck!